Hello and welcome to G Fun Facts Online. Every great leap in science, from Galileo's telescope to the Hubble Space Telescope, has been powered by a new tool that let us see the universe in a new way. Today, the next great tool isn't a lens, but a new way of thinking about computer memory. Scientific AI is poised to cure diseases, model our climate, and unlock the secrets of the cosmos, but it's hitting a wall. A digital memory wall. The machines we use for our biggest questions are running out of memory, and it's slowing down the pace of discovery. But a new technology, a new standard called Compute Express Link, or CXL, is here to tear down that wall. This isn't just a small upgrade, it's a complete redesign of how computers work, creating a future where our ability to discover is no longer limited by memory. Today, we're exploring how CXL is forging the future of scientific AI. To understand why CXL is such a revolution, we first need to grasp the sheer scale of the problem. Modern science is drowning in data. Take genomics. Sequencing a single human genome creates hundreds of gigabytes of data. Now, imagine you're an AI trying to find the genetic marker for a rare disease. You don't just need one genome. You need to analyze the data from hundreds of thousands or even millions of people. That's petabytes of data, thousands of terabytes. These datasets are so enormous, they simply can't fit into the memory of a single computer. This forces researchers to chop up the data, process it in small, slow chunks, and waste valuable time just managing data instead of doing research. Or look to the stars. The Large Hadron Collider at CERN, where scientists smash particles together, generates about 90 petabytes of data every single year. The upcoming Square Kilometre Array telescope will produce more data in one day than the entire internet currently holds. AI is essential to sift through this digital fire hose to find the faint signal of a new particle or a distant cosmic event. These tasks need massive amounts of memory that can be accessed instantly. Then there's climate science. The climate models that predict hurricanes and long-term global warming are incredibly complex. They need to hold a digital version of the entire planet, oceans, atmosphere, ice caps, in a computer's memory. The more detailed the model, the more memory it needs, and the better our predictions become. Right now, we're limited by how much memory we can cram into a single system. And in medicine, AI is helping us discover new drugs by simulating how a molecule interacts with a protein in the body. This involves calculating the forces between millions of atoms. The bottleneck? You guessed it, the amount of memory available to the processor running the simulation. This collision between massive data and limited hardware has a name: the memory wall. It's not a physical wall, but a set of 4 critical problems in how our computers are built. First, there's the bandwidth bottleneck. Think of it like a highway. We have CPUs with more and more cores, like adding more and more lanes to the highway. But the number of on-ramps to get data from memory hasn't kept up. So you have all these powerful processor cores just sitting idle, stuck in traffic, waiting for data. Second is the capacity ceiling. A computer motherboard has a fixed number of slots for memory sticks, or DIMs. Once you fill them up, that's it. To get more memory, you have to buy a whole new, more expensive server. This creates a hard limit on the size of a problem you can tackle on one machine. Third, we have a huge problem with stranded and underutilized memory. In a data center, each server has its own island of memory. If your server runs out of memory, it can't borrow from the server next door, even if that server is mostly idle and has tons of memory to spare. It's like living in a neighborhood where every house has its own well, but you can't get a glass of water from your neighbor if your well runs dry. This is incredibly inefficient and expensive. Finally, there's the latency gap. When a processor can't find the data it needs in its fast local memory, it has to go fetch it from somewhere slower, like a solid-state drive, or SSD. The performance penalty for this is devastating. It's like the difference between grabbing a book from the desk in front of you versus having to drive to a library in another city to get it. The computation grinds to a halt. Scientists need a new architecture where memory isn't a fixed local island, but a fluid, shareable ocean. This is exactly what CXL delivers. At its heart, Compute Express Link is a high-speed connection built on top of the familiar PCI Express or PCIe standard. That's the slot on a motherboard where you plug in graphics cards or network cards. Using PCIe as the physical foundation is a brilliant move because the industry already knows how to build it, making CXL cheaper and faster to adopt. But CXL isn't just a faster PCIe. It introduces a new set of rules, a new language, that changes how processors, accelerators like GPUs and memory all talk to each other. CXL has three key protocols that work together over a single link. The first is CXL.io. This is the basic protocol. It handles discovering and setting up devices, just like standard PCIe. It's the foundation that ensures everything is compatible. The second protocol is CXL.cache. This is a game changer. In modern science, we use a mix of CPUs and specialized accelerators like GPUs. Normally, for a GPU to work on data, the CPU has to copy it from its main memory over to the GPU's memory. This is slow. CXL.cache creates a system where the CPU and the GPU can both look at the same data in the same place, ensuring they always have the most up-to-date version. It eliminates all that slow, manual copying, which dramatically speeds things up. The third and most revolutionary protocol is CXL.mem. This is what truly smashes the memory capacity ceiling. CXL.mem allows a CPU to treat memory on an external CXL device as if it were its own local memory. This means you can plug a card full of memory into a PCIe slot, and the CPU can access it seamlessly, breaking free from the limits of the motherboard's memory slots. To make this work, CXL defines three types of devices. Type 1 devices are accelerators, like a smart network card, that don't have their own memory. They use CXL.cache to work directly on the CPU's memory. Type 2 devices are accelerators that do have their own memory, like a high-end GPU. They use all three CXL protocols, creating a unified memory space where the CPU can see the GPU's memory, and the GPU can see the CPU's memory. It's a true two-way street. And finally, there are Type 3 devices, which are often just called CXL memory expanders. Their only job is to provide huge amounts of memory to the CPU. These are the devices that let you add terabytes of memory to a server with a simple plug-in card. This new CXL language and these new devices enable a complete architectural revolution. We move from a world of rigid, isolated computers to a world of disaggregation and composition. This leads to three incredible new concepts: memory expansion, memory pooling, and memory sharing. Let's start with memory expansion. This is the most direct benefit of CXL. Using a Type 3 CXL memory expander card, you can take a server that was limited to, say, 1 terabyte of memory and easily expand it to 4, 8, or even 16 terabytes. While this CXL-attached memory is a tiny bit slower than the memory plugged directly into the CPU socket, it is orders of magnitude faster than fetching data from an SSD. It creates a new, massive, and fast tier of memory. For a scientist, this means that a genomic dataset or a climate model that was just a little too big to fit in memory no longer requires a painful, slow workaround. They can now run their entire analysis in memory, which is exponentially faster. CXL 2.0 takes this a step further with memory pooling. It introduces a CXL switch, which works just like a network switch, but for memory. This allows you to create a central pool of memory that can be shared among many servers in a rack. Think of it like a memory library for your data center. A genomics server might need 4 terabytes of memory for a big job. The CXL switch allocates it that memory from the pool. When it's done, it returns the memory to the library. Then, a climate modeling server in the same rack can check out 6 terabytes of memory for its simulation. This is a paradigm shift. Data centers no longer need to over-provision every single server with expensive memory that sits idle most of the time. They can have a central pool and allocate resources dynamically. This ends the problem of stranded memory and dramatically lowers costs. Then comes CXL 3.0, which enables true memory sharing. While pooling lets one server own a chunk of memory at a time, sharing allows multiple servers to access the very same piece of memory at the very same time, with the hardware guaranteeing everything stays in sync. This is profound. Imagine a complex physics simulation. One powerful CPU-based server is running the simulation and writing its results into a shared CXL memory device. At the same time, a second server packed with GPUs is reading that data in real time to visualize it and run AI analysis on it. There are no network transfers, no slow data copies. The GPU server sees the results the instant the CPU server writes them. This creates a single, logical supercomputer out of what used to be separate machines, enabling a level of collaboration between processors that was never before possible. So how does this new blueprint change the day-to-day work of scientists? Let's revisit our examples. For genomics researchers, CXL expansion means they can create servers with tens of terabytes of memory. They can load entire population-scale genomic databases, like the UK Biobank, into a single machine's memory. Analyses that used to take days of shuffling data from slow disks can now be done in hours. Using CXL pooling, an entire multi-step bioinformatics pipeline can be optimized, allocating huge amounts of memory for one step, then releasing it and allocating a smaller amount for the next, all from the same central pool. For climate scientists, CXL means they can finally run the ultra-high-resolution simulations they've dreamed of. The accuracy of a climate model is directly tied to its resolution, and memory has always been the constraint. With CXL, they can build machines to hold a much more detailed model of the entire Earth system, leading to better predictions of extreme weather and the impacts of climate change. With CXL sharing, they can even have an AI constantly watching the simulation in real time, identifying patterns and improving the model as it runs. In drug discovery, AI models screen billions of virtual molecules to find a potential new medicine. This is a job for GPUs, but they have limited onboard memory. With CXL, a GPU can treat the host server's massive CXL expanded memory as its own backyard. It can work on molecular models or training sets far larger than what could fit in its own memory, dramatically accelerating the search for new cures. And for the physicists at the Large Hadron Collider, CXL offers a way to build smarter, faster trigger systems to filter the petabytes of data they generate every second. They can create a fabric of CPUs, GPUs, and other specialized processors, all analyzing the same incoming data from a shared CXL memory pool without making redundant copies. This maximizes their chances of catching a fleeting glimpse of a new fundamental particle of the universe. This isn't just a theory on a whiteboard. The CXL ecosystem is growing rapidly. Intel's Sapphire Rapids and AMD's Genoa server processors already support CXL. Memory makers like Samsung and Micron are shipping CXL memory expander modules right now. And crucially, the open source community has been hard at work adding robust support for CXL into the Linux kernel, the operating system that powers most of the world's scientific computing. This means the software is ready for the hardware. Now, the road ahead isn't without challenges. CXL memory is still a bit slower than native memory. so software needs to be smart about where it places data. The software tools for managing these complex dynamic memory fabrics are still maturing. And sharing memory between different systems introduces new security considerations that need to be carefully addressed. But the trajectory is clear. CXL is dismantling the rigid, inefficient architecture of the past and providing a new blueprint for the future. It's a future of disaggregation, where data centers are built from flexible pools of processing, memory, and storage that can be assembled on the fly to create the perfect machine for any scientific problem. The history of science is a story of overcoming limitations. The memory wall was a symptom of our own success, a sign that we were generating data faster than our old tools could handle. Compute Express Link is the new tool designed for this new era. It gives scientists the freedom to stop worrying about the limitations of their computers and start focusing on the limitless potential of their questions. It is the architectural foundation upon which the unimagined discoveries of tomorrow will be built. Thanks for tuning in to G Fun Facts Online.